lesson today. I will not keep it so long, so if you want to practice on your own. But let us start about the theorem. It's a very, very helpful theorem, and that is related to some angles that you can consider in circles. Okay, so let us have a circle here. There are some things that I just want to recap from what you know about circles. Yes. So assume that you have a circle. There is a point here. What is the meaning of a circle, by the way? So if I consider this, the circle is the set of points on the plane whose distance of those points to some fixed point on the plane is a fixed number. Yes? So, and that fixed number is called the radius. So for example, if I take this one, I don't know, if I measure this, whatever the length of this one is, if I change my point to here, and I take this one and measure that, that length and that length would be the same, and it doesn't matter which point I am choosing on the circle, these distances are all the same number, and that number is called the radius. Yes. Of course, there are some terminologies you need to know about circles. This radius is usually denoted by capital R or sometimes little r, depending on the context, so it doesn't matter for the time being, you just call it R. And then you know that the area of the circle probably is famous for you. Let me pick this only, this PR squared, and if I ask you what is the circumference or perimeter of the circle, so I don't know how you denote it, but you can say, I don't know, there is no standard notation for the parameter, so if you just say it, a parameter, for example, P is 2 pi r, yes. And then you know that 2 times a radius is called the diameter of the circle. So from here to here is 1 radius. If I continue it, the whole length is a diameter, sorry. And that diameter is actually 2 times r. And then this part of the circle that you see is called an arc. Yes. So the biggest arc is the circle itself. Yes. So that is an arc. But there is also a notion of chord. What is the chord? The chord is, what is a chord? It means that you take 2 points on the circle and just immediately connect them together. This line that you see is called a chord. So apparently you see that this arc is longer than that chord. In which sense? In the sense that if you bend a string so that the string overlaps with the circle, and then whenever it is finished, cut that string and stretch it and measure the length. That length that you get is in the unit of length, and that is called the arc length. Yes. So the arc length is different from this length from here to here. So it means that if you consider an ant moving on the circle, the distance that the ant travels from this point to that point is the arc length between these 2 points. Yes, that's the meaning of an arc length. So that's also a notion of the chord. And if you consider the whole part here, this is called a sector. If you consider this one, this colored area, this is called a sector of the circle. Yes. But in this course, I want to introduce you 2 types of angles for circles. One of them is called a central angle, and one of them is called an inscribed angle. So what do I mean by that? So if you have a circle, yes, here, if you consider 2 radii, by the way, the plural form of the radius is radii, yes? It means that 2 or more radii, yes? Okay, so if I take 2 radii from the circle, these 2 radii make 2 angles for me. but be careful. The vertex I am considering to be the center. This angle, let me call it alpha, or the bigger angle, let me call it beta. These two angles are called central angles. Okay? Alpha and beta, central angles. Yes? So a central angle is an angle whose vertex is at the center and the arms are radii of the circle. But what is an inscribed circle? An inscribed angle. An inscribed angle is an angle whose vertex is on the circle itself somewhere. Okay? So I take a point on the circle, so let me call it A. Then I draw two chords passing through A. So one chord is here, for example, the other one is there. Then this makes me one angle only inside the circle. This angle, let me call it theta. This is called an inscribed angle. Yes, so theta, an inscribed angle. So the whole point is that the vertex should be on the circle and the arms are chords of the circle. But in the case of central one, the center is at the center, the vertex is at the center of the circle and the arms are radii. Is that clear? It's the definition of inscribed circle, inscribed angle and central angle. But there is a very nice relation between central angles and inscribed angles that are subtending the same arc. By the way, that is also the terminology in English. I don't know how is it in Swedish, but this I want you to know. So this arc, we say that this theta subtends BC, this arc. Okay, and thereby, I don't see it in your book, but this is the symbol that we use for arcs, yes? So we say that BC arc is subtended by the theta, or theta subtends BC. Okay, so here in this case the same, yes?
How do we know if the arcs that you mean by the arc BC is the one?
Yes, the one that I showed by hand. But of course you are right, because you can also consider this as an arc. But this arc is not the one subtended by this inscribed angle. Yes. Here you are right. The arc subtended by alpha is this blue one. This is the arc subtended by alpha, or I would say alpha subtends this arc. And this bigger one, the black one, is subtended by beta. Yes? But in that case, there are no other angles. The other angle will be outside the circle, so I don't care about it. But you are right. In principle, when I say arc BC, it is not clear, do I mean this one or I mean that one. Sometimes people differentiate it. If they really mean that, they call it BAC arc. Then people realize it means this. Yes. Yeah. Okay. But these are small matters, so let us understand what is the main concept here. So that's a very nice theorem, okay, and that is called Inscribed-Angle Theorem. So this means that if I have two angles, one central and one inscribed, but both subtending the same arc, then the inscribed one is half of the central one. Okay, so what does it mean? It means that, let me, for example, draw a random central angle for you here. This one. Let me call this one alpha. So this is the arc subtended. Let me make it thicker. So this is the arc subtended by angle alpha. Now let us draw another inscribed angle, which is subtending the same arc. For example, let me take this random point here on the circle, but let me draw these two chords. Yes? So you see, both of them, this angle, let me call it beta. This angle is inscribed angle subtending this arc. This angle is central and subtending the same arc. If they are subtending the same arcs, then alpha is 2 times larger than beta, and exactly 2 times. Okay? So this is the content of Inscribed-Angle Theorem. So that is what we want to prove. Okay? First of all, tell me, is the statement clear? For example, by the way, you don't need to just draw that one. So for example, I can take this one. It's probably this one. Yeah, something like this. Okay, so that is very interesting. So if I call this gamma, gamma is also half of alpha. So this means that gamma and beta are exactly equal. So that is the content of this theorem. Okay, is that clear? So here, if I want to add to this list, I would say that if this is the picture that I have, 2 of them are inscribed, but opposite to the same arc, or subtending the same arc. So this is equal to 2 gamma. This means that beta and gamma are also equal to themselves. But we want to see why this is the case. Yes?
I don't exactly get how the term subtend is used. Like, or did you say that beta is subtending some?
Yes. If I start with the angle, I use it in an active voice.
But
I say beta subtends.
Subtends,
the
but
arc.
what, like, or is it, does it subtend the, like, the arc?
Yes.
That,
Yes.
but then could it be any arbitrary, like, curve that it subtends, or should it be specifically an arc of a circle?
Arc of a circle, I've heard.
Yeah.
I haven't heard about subtending an arbitrary curve.
And, like, could it be between the 2 points of an arc and any arbitrary point at all, or should it, that's like inside the circle? Could we, for example, if we have a point between alpha and beta, and connect the 2 points to the arc?
No, what I say that I start with the circle, so I cannot change the circle in the middle. I have a fixed circle, and then I fix a point on the circle. Yes.
Mm-hmm.
And then I took 2 points. No, I take 2 points on the circle and another point on the circle to serve as the vertex. Then I connect that point to these 2 points. There would be one part of this circle, which is inside my angle.
Wait,
The angle.
does alpha subtend the curve?
Alpha also subtends the same arc. But this is a central angle subtending. Alpha, this point is the center. It's not arbitrary.
So could we, but we couldn't, like, in theory, have a point between alpha and beta, which would also be connected to the same 2 points.
Yes, but this terminology is used for either a central angle or an inscribed angle.
Okay.
In a way that we can state something.
Okay, then.
Yeah.
Okay, understand.
Okay, but let us see why this is true. Okay? We can consider some scenarios because we have to make sure that this will work for all cases. One thing that we can do is to consider a special case first. What is that special case? A special case is that, let me consider this scenario, that I have this central angle, alpha. For the time being, let us consider that one of the sides of the inscribed angle is actually a diameter. So what does it mean? I'm considering one special case. So for example, let me just continue this, and I get this point, let me call it A, this is O, this is B, and this is C, and I connect this one to this one. So you see, in this way, you see that you have an inscribed angle beta, you have a central angle alpha, but this doesn't consider all scenarios, yes, because I am considering a very particular form of inscribed angle in which one arm is actually a diameter. Okay? So let us consider this case first and convince ourselves that this alpha is indeed, in this particular case, is 2 times larger than beta. This is extremely simple. Why this is the case? Why do you think alpha is 2 times larger than beta? Almost obvious. Remember, O is the center. Why beta is 2 times? Why alpha is 2 times larger than beta? Let me give this a name. Let me call this one myself gamma. But what type of angle is this angle for this triangle? Exterior. Yes? So this alpha is an exterior angle to this triangle. So I would say that alpha, according to that theorem, is beta plus gamma. Yes? But you need to, I just mentioned it orally, but in the exam you have to write, you have to say that alpha is an exterior angle for the triangle OAC, therefore alpha is beta plus gamma. But now, you see, I have just claimed that beta and gamma are the equal. It's very obvious, isn't it? Why alpha, why gamma and beta are equal? Yes, why they are equal?
No, it's an isosceles triangle.
It's an isosceles triangle. Because if I ask you what is OC, you tell me it's the radius. If I ask you what is OA, you tell me it's the radius. And then you know that 2 radii of the same circle are equal in size. Yes? So this means that OA is equal to OC, both radii. Both radius,
I think it's radii.
radii, yes. Both radii, did I write it wrong? Yes. Radii, both radii of the same circle. Yes? So this means that beta is equal to gamma. Okay? On the one hand, alpha is beta plus gamma. On the other hand, gamma is equal to beta. So what does this mean? This means that alpha is 2 times larger than beta. Oh, sorry. Yes, alpha is 2 times larger than beta. Is that clear? So this was very, very simple. But this doesn't consider all cases. It only considers this scenario, that my inscribed angle is the one that one of the arms of that is a diagonal. Is a diameter. I don't know why I'm confusing the words today. Okay, but let me try to understand this problem for a different setup. Okay, so let me just move a little bit here. Then what happens? I still want to convince myself that this is still true. You know, I take this circle, and then what I have a central angle here. But this time, let me consider this inscribed one. For example, the one that I have here. Yes? So I want you to tell me why this time again the same works. Because the picture is different. I will call this as before beta. I will call this as before alpha, and this is O. This picture is different from this one, so not exactly the same idea will work, but I'm just claiming that again it is true. Alpha is still 2 times larger than beta. This is another scenario that we have to consider. Yes. Why this is true for this one as well? The trick is to use the previous one. Remember, in the previous one, we learned that if I have an inscribed angle subtending the same arc as my central angle, provided that one side is a diameter, then alpha is 2 times beta. Yes, Oscar?
Draw a diameter that has to beta.
Yes, exactly, and use this theorem in this way 2 times. Yes. So what we say that, okay, let me just change my color. I would say I will take this point, whatever it is, and I connect it to O and then continue it so that I will have another intersection point on the other side. Yes. Okay, and then you see that alpha will be now divided into 2 alphas, but not necessarily equal. So let me call it alpha 1 and alpha 2. I don't know if they are equal or not. It might be the case or not in general. But one thing, and beta will also be divided into 2 parts, beta 1 and beta 2. So one thing is clear. Beta that I am working with is beta 1 plus beta 2. Alpha that I am working with is alpha 1 plus alpha 2. Okay? But forget about this part of the picture for the time being. Yes? Only concentrate on the right part. On the right part, you have this scenario. Do you agree? Because I have a central angle alpha 2. I have an inscribed angle beta 2 subtending the same arc as alpha 1, alpha 2, but then one arm is the diameter. So this means that, what can I write? According to what I showed for this case, I am certain about this idea that alpha 2 is 2 times beta 2. Yes? Understandable? Because if I ask you what do you have, you will tell me that I have a central angle, I have an inscribed angle, subtending the same arc as the central angle, but one leg is the diameter. Exactly the same thing that I had here. So I can't say that alpha 2 is 2 times larger than beta 2. This I know. But then I will take this one and hide this part and concentrate on the other part. Yes, I can say the same thing. Yes, I can say that, okay, I have a central angle, I have an inscribed angle subtending the same arc as the central angle, but one leg of the inscribed angle is the diameter. So I can use the same one. I will say that, okay, because of the previous method that I showed, alpha 1 is also 2 times beta 1. Yes? And then what I can do, I can add these two side by side. Alpha 1 plus alpha 2 equals to 2 beta 1 plus 2 beta 2. But alpha 1 plus alpha 2, I can factor a 2 out. It becomes 2 beta 1 plus beta 2. And this time alpha 1 plus alpha 2 is nothing except alpha. Alpha 1 plus alpha 2 is the original alpha. I can call it alpha. And then beta 1 plus beta 2 is the original beta. So it is 2 times beta. Yes, so you see that it is extremely important for this theorem to prove this one first. Because in the second scenario, I am using the result of the first step. So it is from logical point of view, you cannot just answer these things randomly. Because you give it in the exam, you have to prove this part first and that part second. But this doesn't cover all scenarios, yes? In the first scenario, I considered about the inscribed angle in which a leg is the diameter. in this case, somehow the central angle is fully inside the inscribed angle. But is there any other scenario that we have to consider? Yeah, it would be partially outside, yes? So we should also consider that. But these are the general things. I don't think we can have any other situation, yes? So what we do, we have to consider the third possibility and show that this is also the case. Because the proofs are not the same, by the way, you see? What I have written on this first column and what I have written on the second column are not a carbon copy paste of each other, yes? I have written something like this, and I have written something differently here. This means that the proofs are different. So I have to consider different cases. So let us consider the last case. You will see that this would be the last. Yes? So I will consider again another circle. Not another, probably you can do the same circle, but let me consider a central angle here. But this time, I want to keep my angle outside, yes? So I want to keep this angle here, for example. Let's make it more clear. Okay, again in this case, this is my beta, and that one is my alpha. Why do you think this is also true? So three different scenarios. In the first two cases, I was able to show that the relation is the same, even though the pictures are different. Here I want to show that again, alpha is 2 times beta, even though this is also different from the previous one. So why do you think this is also correct? That alpha is 2 times larger than beta. So you see that even though this is one theorem, but we really have to consider 3 scenarios because they are different. Why do you think it is true? Okay, again, the same trick will work, yes, as Oskar mentioned for the previous one. So what we do, we take this point again and connect it to this, to the center, and continue it, yes? I get this point. Let us see if I have done it right. Yes, I think it will work. Yeah. Yes, let us see how it works. So this time I have to bring something new in. This angle, let me call it gamma. Yes. Let me see if it works or not. I take this one to be gamma. And then, if you don't mind, I have to change something else here. So let me also call this one something else theta, for example. So we have to be careful not to be confused, okay? Let me see if I can do it myself. So this angle that you see here, this gamma, is an inscribed angle, yes? But one leg of this gamma is of course a chord, but the other one is a diameter. Okay? And then this angle gamma is subtending which arc? Is subtending the arc from here to here. Yes, is that understandable? So this gamma is actually subtending this arc from here to here. what is the central angle subtending this one? The central angle subtending this one is theta plus alpha, the whole angle, yes? Is that understandable? So this means that gamma, alpha plus theta, which is my central angle here, is 2 times gamma. So let me repeat it again. You see, don't get confused. So this is gamma, which is an inscribed angle. One leg of my inscribed angle is this blue line, and the other leg is this diameter. Yes? But according to that previous problem, as soon as one of the legs of my inscribed angle is the diameter, I can say that the angle times 2 is the central angle subtending the same arc. You see, this is the arc subtended by gamma. This would be the arc subtended by this central angle. So gamma is alpha plus theta times, alpha plus theta is 2 times gamma. Is that understandable? Yes? Okay. But the point is that I want somehow to relate it with beta. So what can I write? Okay, so if I want to have beta, I need to take this part away. So there are many names that I have to put here. So let me take this one to be, for example, rho or whatever. I want to take rho away from gamma because I want to talk about beta. But rho is also an inscribed angle. Look, rho is also an inscribed angle, so that one leg of it is a diameter. So this one is also half of the central angle subtending the same arc as this one. What arc rho is subtending is this arc. And then this is exactly the arc subtended by theta as the central angle. So what I can write that theta is 2 times rho. Okay? I don't know, it's a little bit complicated, but I hope that you understand. If not, you can ask me again. Let me just put and prove it and finish it. So then, instead of this theta, I put 2 rho. So this becomes alpha plus 2 rho is equal to 2 gamma. I move, what is alpha? So I wasn't able, no, might be, I am also confused myself, let me see. What I have done is right, alpha plus beta is 2 gamma, that is correct. So let me just do this like this. Because I want to bring beta in, I don't want to get rid of alpha. So let me copy and paste this one, alpha. Instead of theta, what can I write? I can just simply write 2 rho. Instead of 2 gamma, but you see on the picture, gamma is rho plus beta. And then I multiply it. Alpha plus 2 rho is 2 rho plus 2 beta. And then 2 rho and 2 rho are cancelled. Again, I get the same thing that I want. Alpha is 2 beta. Yes? So let me just repeat this. Might be it's a little bit. Let me repeat everything. Okay. So originally you have only this black angle, alpha, and this blue angle, beta. You want to show that alpha is 2 times larger than beta. This is your question. Okay? So what I did, I took this vertex of the blue angle, joined it to the center, and continued this until I get this point. Okay? Now, I have a big angle here, which I call it gamma. If I ask you what type of angle gamma is, you can immediately answer, because gamma has 2 legs. One of them is this one, which is a chord, and the other one is this one, which is also a chord, but better than that, we can say it's a diameter. Yes? So this means that the arc subtended by angle gamma starts from here and goes up to here. This arc that you see here is in front of gamma. Okay? Now, can you tell me a central angle subtending to this one? You would say yes. The angle that starts from here up to here, you see one leg is here, so this is the point. Another leg is here, so that is the point. So this arc, the red one, is also subtended by this big central angle, which is nothing except alpha plus theta. So on the one hand, I have the inscribed angle gamma. On the other hand, I have the central angle alpha plus theta. But one leg of the inscribed angle is diameter. Based on the first scenario, I am sure that this one plus that one is equal to 2 times that one. This is from the first scenario. Okay? But now, let us change my strategy a little bit. Instead of looking at gamma, let me now look at rho, this angle. This leg is a chord. This leg is also a chord, but also more. Yes, it's a diameter. So rho is an inscribed angle, but this is subtending this arc this time. Yes? Now, theta itself is also a central angle subtending the same arc up to here. And one leg is the diameter. So again, I can use the same scenario and I can write that 2 rho is equal to what? 2 rho is equal to theta. Yes? Okay, might be I made it a little bit harder here. One other way is to subtract these two instead of adding them. Another way. I subtract this one from that one by factoring a 2 out. It becomes gamma minus rho. On the right hand side, if I write this and take this away, theta and theta are gone. What is left is alpha. But look at the picture now. Gamma is from here to here. Rho is from here to here. If I take rho away from gamma, what is left for me is just beta. So this one is nothing except beta. So this means 2 times beta is alpha. Yes? So this means that hopefully now you are satisfied that in all possible scenarios, even though it was a little bit harder to visualize it here, but in all possible cases that can happen, the same statement is true. The central angle is 2 times larger than the inscribed angle subtending to the same arc. Yes? Okay. This is you need to know. So from now on, this picture is a good picture to have in mind. So if you have a circle, I don't know, for example, if I just draw this one for you, and I don't know, randomly draw this one for you, what can you say about alpha and beta? What can you say about alpha and beta? Yes?
They're equal.
They are equal. Even though there is no notion of central angle here, but who cares, yes? There is an angle. So I take this one and that one. For example, if you want to understand why they are equal, but I want you to immediately understand without spending time on it. If you see this picture, immediately conclude that alpha is equal to beta. If you want to understand why, you would say that, okay, I will find the center, and I connect the center to this one and that one. Yes? And then you call this one, for example, gamma. Gamma is 2 times larger than beta. Why? Because gamma is central, beta is inscribed, but they are opposite to the same arc. And then you can say the same thing for alpha and gamma. Gamma is also equal to 2 alpha. But it means that 2 alpha is equal to 2 beta, so this means, as you said, alpha is equal to beta. But if you really, of course, this is the reason why this is true, but you can use it without every time mentioning it. Okay, so this is the way that you need to look at this problem. So if I take these two away, so if I call this one rho and if I call this one theta, what is the relation between rho and theta? They're also equal.
So this means that these triangles are similar.
Yes, definitely. So this means that whenever I draw two chords intersecting, the triangles that I get are similar, and that would be the topic of the next lesson. I don't want to continue for that, but you can call it butterfly theorem because it's like the butterfly, okay? Something like that. Anyway, so I want you to immediately understand that. There is another thing that I want you to understand that is also very important. Very simple facts, but very important. Assume that I have a diameter. A diameter. That's the longest chord. And then I pick a random point on one of these semicircles. For example, this one. Let me take a random point on this upper semicircle. And then I connect it to this point and connect it to that point. What can you say about this angle? It's a very, very simple but very important idea that I want you to remember by heart. So I just draw a diameter, whatever the diameter is doesn't matter, and then I pick a random point on one of these semicircles and then connect that point to the end points, and then I make an inscribed angle. Okay, it's an inscribed angle. But there is something very nice about this angle. What is the measure of that angle?
90.
It's 90. But why? It's always 90. The reason is that this angle is an inscribed angle subtending this big arc. Yes? But this angle that you see here, on the one hand is how much? Is 180 degrees. On the other hand, this is a central angle subtending the same arc. So this means that this alpha times 2 is 180. So this means alpha itself is 90 degrees. Yes, is that understandable? It's an extremely simple but important thing. So you see, it doesn't matter. If I choose any point, I do that. This is again 90. If I choose this point, I do that. This is again 90. Yes? So all these angles that you see are 90 degrees because all of them are inscribed angles. They are all subtending the same arc, but this arc is subtended by this central angle, which is 180. So the value of each one of these angles are 90. Any questions? Yes? There is only one thing that I want to mention, then we can solve some problems together and then the lesson is finished. So one thing that is good to know is that what happens if I have a quadrilateral inscribed in a circle? This is something that I want you to understand. What do I mean by inscribing a polygon in a circle? Yes, if you have a circle, when I ask you to inscribe a polygon here, it means draw the polygon in a way that the vertices all lie on the circle. But sometimes, of course, it is not possible at all. Yes. So this is you cannot satisfy this condition for any polygons. For example, if you have a rhombus like this, very narrow rhombus, I say very narrow because I want you to visualize that. It is not possible to draw a circle that passes through all the vertices simultaneously. This is not possible unless this rhombus has a particular form. For example, if the rhombus is a square, of course it is possible. But in general, it is not possible. There are theorems in more advanced geometry talks about these things, but that is not my concern here. My concern here about the book is that if you already have a quadrilateral that you know it is inscribed in a circle. Okay? We don't want to talk about the conditions that I have to impose on quadrilaterals to make them inscribed quadrilateral. No, forget about those things. The questions are simpler for your case. You have an inscribed quadrilateral. Whatever you have here, any form of quadrilateral, but which is inscribed, means that you are able to find a circle which passes through all the points A, B, C, and D. There is a very nice relation which is in general not true for any quadrilateral. The relation is that there is a relation between the sum of these two angles. Okay, so what is the sum of these two angles? Of course, if I find the sum of these two angles, I can immediately find the sum of these two angles as well, because I know that the sum of the angles should be 360 degrees. So if I can find the sum of these two, automatically I also find the sum of the other two. Okay? So, what is this sum? What is this sum? You see, I don't know anything about my quadrilateral. It could be different, but no matter how I inscribe it, this angle plus that angle is always 180. That is important, which is not trivial. But why this is the case? Why do you think that in this picture, this angle A plus this angle C is 180? And of course, this means that the sum of the other two should also be 180. Why this is true, do you think? Yes?
You have two arcs
Yes?
for the both two angles, and those two arcs together are 360 degrees.
Yes?
And 360 is supposed to be 2 times those two angles.
To be honest, this is the way that I do it myself, but this is not the way that you learn it in Math 2C.
Okay.
Because you are talking about the measure of an arc. It's a little bit ambiguous.
Okay.
Because you know that if you have different circles, so for example, if I have this circle, and let me consider the same center and make the circle smaller, okay? And then I draw, for example, 30-degree angle here. This 30-degree angle will subtend this arc from the smaller one. It subtends this arc from the bigger one. There are two types of numbers that can measure the size. Okay, which one is bigger? Okay, if you consider about something which is called the measure of an angle, I would say that this angle and that angle are the same. Yes, not because they have the same length. The length of this one is greater than the length of this one, that's clear. But because they are subtending the same central angle, I would say that these two arcs are of the same size somehow. Okay? And that is a little bit confusing, understandably, yes? This is why your book, I think wisely, doesn't want to talk about the arc lengths, yes, or the arc size. So they want to connect everything with the central angle. So what you said is completely correct. So what you said that this is an inscribed angle, and this is the subtended arc. Remember this in your head. And this one is also an inscribed angle, but this one is the subtended arc. And then in your head, you are adding this subtended arc to this subtended arc, so it becomes the full circle. And then you say that because this is an inscribed, and full circle is 360 degrees, and then because this is inscribed, you divide it by 2. It's not wrong. But what I'm saying is that we don't know about this side. For example, in other books they say that the angle A is equal to 1/2 of an arc. Okay, but they want to avoid this for understanding reasons. Okay, can you repeat this process but somehow connect it with the central angle somehow? What you say, if you want to understand it in your lesson, you would say that, okay, I will take the center, there is one center here, let me call the center O, and then I connect O to D, I connect O to B. And then what is happening, this angle, let me call it alpha, this angle, let me call it beta. Can I say that alpha is 2 times beta or not? The answer is yes, because this angle alpha is central, this beta is inscribed, but both of them are subtending the same arc. You see, between these two dotted lines I have this blue arc, between these two solid black lines I have the same arc. So this means that this is inscribed, this is central, subtending the same arc, so I can write alpha is 2 beta. Yes? But then, let us try to repeat it the other way around. This one, I call it lambda, for example, and this one, I will call it gamma this time. So don't get confused, yes? This gamma is central. Which arc is subtended by this central angle? This arc is subtended by this central angle gamma. But this lambda is inscribed. What arc is subtended by gamma? The same arc. So this means that, again, because of that theorem, gamma is 2 times lambda. Yes? So do you understand? Because I don't know, from psychological point of view, for people are easier to understand that beta is half of alpha, but if you see the picture the other way around, it would be a little bit hard. So if you want, I can draw the picture here for you to understand what I mean. So here you have this. So for example, let me just draw something like this. No, it's not working like that. So I want to have this, okay, and then I want to have, okay, I want to have this, exactly like this. So you see, if I give you this angle to be x, if I call this angle to be y, I want you to tell me that you really understand why y is 2 times x. Do you understand that? Yes? Because x, if I call what type of angle is x, you would say this is one leg, it's a chord, one leg, it's a chord, so this is an inscribed angle. If I ask you what type of angle is y, you would say this is a radius, that is also a radius, and that is center. So y is a central angle. This is what we understand first. Secondly, if I ask you, can you show me the arc which is subtended by x, you would say that this is the leg of x here, and this is another leg of x here. So this arc, that I am making it clear now, is the arc subtended by x. If I ask you the same question, can you show me the arc subtended by y, you would say this is one leg of y, and this is the intersection point, and this is another leg of y, this is the intersection point. So this means that the same arc, you see, is subtended by y. So this means that this is central subtending this arc, this is inscribed subtending this arc, so y is 2x. Yes? So this I want you to get familiar. If you think that you will forget, draw this picture somewhere in your notebook. Yes? For many people it is easier to, I don't know, when it comes to this context, it is easier to think about acute angles, but when it comes to obtuse angle, might be get confused. But anyway, hopefully now you understand what I have written here is correct. And then I ask you to add them side by side. So alpha plus gamma is 2 factorized, beta plus lambda. But now alpha plus gamma are angles, not arcs. So you see, well, you just talked about arcs. That is correct. But if you want to tell something in the level of Math 2C, it's better to add angles. Now I'm asking you, if this angle is being added to that angle, what would be the result? I'm adding angles now, so it becomes 360 degrees. So I just changed the way that you express the reason in the form of angles. It becomes 2 beta plus gamma, beta plus lambda, and I divide everything by 2. So your idea is correct, but expressed in a level that we study in Math 2C. Okay, so remember, this is also very important. By the way, this is not always true in any triangles. In any quadrilaterals. Don't get confused. This is a quadrilateral. I know the sum of all of them are equal to 360 degrees. There is no guarantee the sum of these two should be 180 and the sum of these two should be 180. Some cases this is the case, some cases this is not. But if I have this scenario that all of them are on the circle, then yes, that is true. Always this is true. For example, in a parallelogram, I know this one plus this one is always 180. But this one plus the opposite one, it is more than 180 in that case. So remember, don't get confused. For every quadrilateral, what I know is the sum of all angles is 360 degrees. But if my quadrilateral happens to be of this type, that I can find a circle passing through all of them, I have something more to say. What is that? I can say that the sum of the opposite angles are also equal to 180 degrees. That is what I can say for this particular type of quadrilaterals. Okay? Any questions? Okay, so I want you to remember all these things. So these are very simple ideas, but very handy when it comes to geometry. Okay. Let me solve one problem, which is an example in the book, to see how it goes. So I see this picture in the book, if I can draw it more or less the same. So this is one side, and then you have 130 degrees here, and then this is, I don't know, in principle I don't know, because I think in Swedish center is denoted by M. They haven't mentioned, but in principle they should mention that this point is the center. So let me call it C for center, okay? And then you have this one to be V, and then they ask you to find this. Of course, this is extremely simple, I think. This is V, and this is center. You are supposed to find U and V. Very, very simple, by the way. For V, I just told you, this is extremely important to be able to immediately understand what is V. What is V?
50.
Oh, sorry, which one is U and which one is V? Sorry, my handwriting is awful here. So U, yes. So what did you say? 50? Yes, that is correct. Because you see, you can forget about the below part, the part below. You can concentrate on these 4 points. So this means that you have a quadrilateral which is inscribed in a circle. Why? Because I see that all vertices lie on one circle. In that case, I can immediately tell that this V and this opposite one should add up to 180. But this means that V is 50. But U is 90. Why? Because it is inscribed opposite to a diameter. I told you that any inscribed angle opposite to a diameter is actually 90. Why is that the case? If you want to understand why, because you need to consider this angle, which is central and subtending this arc. and it is already 180, we know. And this is inscribed and subtending the same arc. So the size of this is half of the size of the central angle corresponding to it. So it becomes 90. That's very simple problem. So you will not learn, of course, unless you solve problems yourself. Yes, yeah, I will keep the rest. It's very little bit. I think we can solve some harder problems later. Yeah, I would recommend. I will start updating the Google Classroom, and then you can work on the problems. There is one problem set here. Thank you. Any questions?